Last topic for this unit, which as we've said is a little bit of an all over the place unit, but we have so far talked about intermolecular forces. We have talked about solids, liquids, and gases and how intermolecular forces relate to which state of matter it is in and to the characteristics of the solids and liquids and gases when they are in those states of matter. We've talked about solutions, and we're going to finish by talking about spectroscopy. And so let's just jump right in and take a look at our PowerPoint. If we can, here we go. Okay, so as I said, it's spectroscopy. You might remember that in Unit 1, we talked about some types of spectroscopy, specifically photoelectron spectroscopy. So today we're talking more about spectroscopy in the visible range of light and in the microwave and infrared region of the electromagnetic spectrum. So let's take a quick review of the electromagnetic spectrum. We know that it goes from really long wavelengths all the way over here with radio waves that can have wavelengths as long as a kilometer, all the way down to the smallest of rays, which would be things like gamma rays. And we know that as the wavelength decreases and frequency increases, that the energy of those waves increases as well. We usually look at things in the visible light spectrum. But today, in talking about spectroscopy, we're going to go down as low as a microwave, which really is what you think of when you think of your microwave oven. It is using microwaves to heat your food, all the way up to ultraviolet light as well. So we use spectroscopy to measure properties that are associated with movement of molecules. Those can be vibrational movement, those can be the movement of electrons. So again, microwaves with our low energy, infrared with kind of a medium low energy, and then visible with relatively high energy, and ultraviolet with higher still. So how does this relate to spectroscopy? Well, we use a lot of different types of spectroscopy. And when we talk about spectroscopy, what we're talking about is generating electromagnetic waves at a particular frequency and then seeing how they are absorbed or reflected by a substance. And so when we use microwave spectroscopy, because it has a very low energy, it's not going to affect the electrons. It's just going to cause molecular rotation. So it's going to move the molecules around. It's going to cause them to turn on their axes. And this is exactly how a microwave heats your food. Because as the microwaves hit your food, they penetrate into the food, they cause the molecules to vibrate and to rotate. And that movement, as we know, that kinetic energy is temperature. And so it heats your food up. We use microwave spectroscopy to look at molecular rotation. Now, when we look at infrared spectroscopy, it has a slightly higher energy than the microwave. And so it's associated with molecular vibration. And when we talk about that, we're talking about the movement within the bonds. So this could be a stretching of the bond itself, getting longer and shorter. It could be a bending of the bond so that the molecules get closer and then farther away. There are a lot of different ways that molecules can vibrate. But this vibration tells us about the type of bonds within a molecule. And so we learn to associate certain peaks with certain bond types and bond lengths. So infrared spectroscopy is used to tell us about the structure of molecules because it detects the different types of bonds present in a molecule. And then the third type of spectroscopy that we're going to talk about today is what we call UV or visible spectroscopy. And this UV or visible spectroscopy, you might remember from photoelectron spectroscopy because it causes electron transitions. This is when the electrons are excited, and so they move up from one energy level to another. And then once that excitement passes, they drop back down and they emit light. And so UV and visible spectroscopy is looking at electron transitions. So not looking at rotational movement of molecules like microwave or movement of the bonds, vibrational movement like infrared, but actually on those transitions of the electrons. So, how does it work? Well, when we have UV visible spectrometry or spectrophotometry or spectroscopy, all of which mean the same thing, light passes through a cuvette. So this is like a little square test tube that contains the sample. The sample then absorbs the light and the detector measures the light passing through the sample. And we have a couple of different kinds of UV vis spectrometers. So some of them are single wavelength. So in that case, we have a light source, it passes through a slit, and that gives us a single wavelength of light that passes through the sample and is detected. So this is the type of spectrophotometer that we have in the lab. Ours can actually generate 4 different wavelengths, but we're measuring the absorbance at a particular color of visible light. There's also UV vis spectrophotometers that can measure the entire range of visible and UV light and then measure the amount of light that passes through. This light, the amount of light that passes through, is directly proportional to concentration. And so spectrophotometry can be used along with something called Beer's law to determine concentration of a sample. And so the way that that works is that we set up a series of standards. We use dilution to create our series of standards, and we measure absorbance. So that's the amount of light that is absorbed by the sample. So we're actually measuring how much we put in, how much we get out, and the difference, of course, is the absorbance, how much was absorbed. And by creating this set of standards, we create a way that we can correlate absorbance with concentration. So then we can put an unknown into the cuvette, into the sample, and measure the absorbance. And we can use that absorbance to determine the concentration of the unknown. And so, for example, if we have this graph, we have an absorbance versus concentration graph given here, and our student is trying to determine the concentration of an unknown substance. Our student measures the absorbance to be 0.4. So we're going to come up here and we're going to look at 0.4 and we're going to come across and we find that 0.4 intersects our line right here. And so we're going to come down to our x-axis and we're going to find that an absorbance of 0.4 correlates to a concentration of 0.28. And so our correct answer is B, 0.28. So we have this linear relationship between absorbance and concentration. So that's our primary application of UV vis spectrophotometry in the arena of solutions, and that is to use it to determine the concentration of an unknown by creating a set of standards and measuring against those standards. Okay, one last topic, and this is the idea of the photoelectric effect. So the photoelectric effect, you might remember from honors chemistry, is the idea that when light shines on a surface, particularly on a metallic surface, that at times an electron can be ejected from that surface. And we can measure the speed of that electron, and therefore we can determine the energy of that electron. But what scientists found is that if the frequency was below a certain frequency, it didn't matter how intense the light was, how bright the light was, electrons were not going to be ejected. And so this is the experiment that confirms the idea of the particle nature of light. And it gives us a direct relationship between the energy of the light and the frequency of the light. And so that relationship is given by the equation E equals H times nu, where E is energy in the units of joules, H is Planck's constant or Planck's constant, which is 6.626 times 10 to the negative 34th joules times seconds, and frequency is in units of hertz or per seconds. So that nu stands for frequency. So we can go back to our photoelectric effect and we can look at the energy of the photon that goes in with this equation, E equals H nu, and we can see that there's a minimum amount of energy required to eject a photon from this surface. And this is actually binding energy. And this is the principle that's used when we do photoelectron spectroscopy, which you might remember from our first unit. So that's spectroscopy in a nutshell. What do you need to know? You need to know that microwaves measure molecular rotation. Infrared measures molecular vibration, so it detects different types of bonds. And UV or visible spectroscopy causes electron transitions and is used to determine the concentration of a solution. As always, if you have any questions, please let me know and have a great evening.